In this video, we will extend the canonical difference-in-difference model, which has two units or two groups and two periods, to a model with multiple time periods. So here, the extension is that we still only have two types of groups, some that get treated and some that do not get treated. But it brings us closer to what we are doing in how difference in difference is done these days. Right? So the first step is to say you have units I who are in treatment groups G, and you observe them in different time periods. And so the example would be workers I who are living in states G, and some states introduce a new policy at some point, and then the workers in those states, after the policy has been introduced, are considered as treated. That's one of the standard questions or standard setups for difference-in-difference design. So how is this usually done empirically? Well, we have a model where you have group fixed effects, and you have a dummy for whether you are post-treatment, and then you have that interaction between group dummies and whether you are post-treatment. So DG here is not really a group dummy, is whether you are in a group that has been treated. Okay, so imagine that of the 50 states, 25 introduce a certain policy, the other 25 don't. Then the dummy DG is 1 if a worker lives in a state that has actually introduced that policy. Now this model still assumes, at least for the interpretation of delta, that all treated groups are treated at the same time. We can extend the model, and this is what we will do in subsequent slides, to cases where you have a staggered adoption of a policy. Okay, and so where you have actually different units or different groups treated at the same at different times. So some states adopt the policy earlier, and some states adopt it later, and some states may never adopt the policy. Also, you often see models whereby you don't have 3 indices like you have in this model, but you simply have 2, whereby each unit is its own group. Right, so you have maybe state level variation in your treatment and in your outcome, and then simply each state is its own group. So that's what I will use from now on. I will simply just have 2 indices here, I and T. So this is still a very simple difference-in-difference model. All units that are getting treated at the same time, and then that parameter delta gives us, by approximation, an estimate for the average treatment effect on the treated, because it tells us again what is the difference in the outcome between treated and untreated after relative to before the treated group got treated. So that's still an estimator for the average treatment effect on the treated. But what you see in typical difference papers these days is something different, is something that looks more like that. The notation may differ, but it looks similar to that, whereby you have typically quite a long panel. So you observe the same units many times. Think about a state panel where you see unemployment rates or GDP over many years in the same states. And what we would do here is we would have unit fixed effects, time fixed effects, and then this treatment indicator, which may or may not vary across states. So what is that treatment indicator? Again, it's it's an interaction term. So that indicator is 1 if you are in a state that eventually got treated, in a period after the state has been treated, and otherwise it's 0. And so here, that general model allows for not only long time windows, so, not only 2 time periods, but many, but it also allows for different units being treated at different times, right? So you may have some units that, if you think about a timeline here, and you have state 1, that may simply, so here we have time, and you simply see that state 1 would have, let's say, if it's a policy that changes the outcomes in that state and improves things, where you would see that jump early because that state adopted the policy earlier, and then the state 2 would adopt the policy later, and we would then see a jump like that if there is an effect. Okay, so basically, for each of those states, that T star is at a different time. All right, so T star 1 and T star 2 are at different times. Okay? And what that indicator is for each observation. So you have to imagine in a panel data set, what it looks like is you have all the, each line is a state year combination, and then you see the outcome in that year, and then you have in the same table that indicator for, well, what state it is in, and an indicator for the year. That's what those two gamma terms are. And then you have your indicator for whether it's in that state after treatment or not. Okay? And so so therefore that indicator varies across states depending on what time what year or what period they have been treated in. And that's called staggered adoption, and that is a very, very common research design that people use. As we will see, it's one that is also a little bit tricky to look at. Now, if you want to go even more flexible here, we, instead of having just one coefficient for post, and that one coefficient for post in the best possible cases, it tells us, if you look at this graph here and you see a jump here and a jump there, in the best possible cases, in the best possible of all cases, it tells us how big the average jump in a treated state is relative to a control group. What that control group is hard to define, which is why this lecture series has not 2 but 5 videos. Okay, but that's the idea, is to look at the average increase or decrease in the outcome after a state has been treated. So it's still, the idea is to estimate an average treatment effect on the treated. And another thing that's important that we typically assume is that once a unit has been treated, it remains treated. So treatment is not revoked. That in most cases is true and applies. There may be cases where it doesn't apply. And there may also be cases, especially in labor and public economics, where the treatment level changes over time. So take, for example, the changes in minimum wages over time. Right, so that there are subsequent changes every couple of years. States change their minimum wage, or think about tax rates or so. They change over time, and if that's the case, you may have to think about what type of difference model you're using. And I can also in a later video I will point you to some literature that provides guidance on that. Okay, but once someone is treated, we assume that they remain treated. Now, what we can also do is we can, instead of just looking at the average difference before and after treated versus untreated or not yet treated units, which is what the previous model told us, we can also look at dynamic affects dynamic responses to the treatment afterwards, and we can also do the same before those states have been treated, which potentially can tell us something about the violation of the parallel trends assumption. So what we do here is we, rather than having just a post dummy that equals 1 if you're after the treatment and 0 if you're before the treatment, you have now dummies for so-called leads and lags. Now, in applied microeconometrics, which DifferenceinDiff belongs to, leads are time periods before the treatment, in the lead up to the treatment. Lags are time periods after the treatment. If you were trained as a time series econometrician, you will find this utterly confusing, because in time series econometrics it's exactly the opposite. Okay, but leads, remember, are those terms in the lead up to the treatment. And so what the idea here is, again, to look at things like we have here, whereby different units are treated at a different time, and we consider for each unit a so-called event window. So we look at, let's say, 3 periods before and 3 periods after, and then we look at the first 2 time periods before treatment, 1 time period before treatment, a time period of treatment, and then 2 after. And we do this for each unit. And what the estimator does is it basically stacks all those units on top of one another. Okay, so rather than having this staggering here, what the estimator does in a nutshell is to put them all, to have the treatment time at t0 and to move them all to the same treatment time. Okay, so you have then state 2 and state 1, and you have state 1 with the jump here, and in state 2 the jump would obviously happen a little bit later, but the estimator, by choosing that event window, does the following: it moves them all to the same event time. So the event time is the time at which the unit has been treated. So to code this, the way we do this is as follows. We have basically a dummy for the first period of the event window. That covers all the periods up until the first period of the event window. The last dummy is 1 for all the periods from the last lag until the end of our sample period. And then you have dummies for any period in between. Okay, so the really interesting dummies are those in between, where you have a separate dummy for each year or each period relative to the treatment period. So you have a dummy that is 1 if you observe the unit in -1, so 1 period before treatment. You have another dummy that is 1 if you observe that particular unit 2 periods before treatment, and then the same for the lags as in after treatment. Okay, so that specification, especially when you have an event window that you consider before and after treatment, and that window is different it happens at different times in different units. That setup you will find very often under the name event study, and we will look at this later in greater detail. But for the moment, what you should be aware of is here we have, again, in our model, in our empirical model, we have the two-way fixed effects. So we have unit and time fixed effects. We identify the effects delta J. So now we have, for each time period, we have a separate effect, and we identify them by the difference between the treated and the untreated groups over time. That at least is the basic idea of that. We will see that the tricky thing about interpreting difference in difference results is that it's not so clear what group over time you compare with what other group. But if you think again about the basic 2x2 difference in difference model, then what those coefficients tell us is basically what is the average difference in the outcome in a given year between the treated and the control group. That's what those coefficients really tell us, right? And I will show you in a couple of slides an example of that. But before we do that, let's just quickly look at the theory a little bit more. So this structure here of coding the data, coding up those dummies, may seem a little bit odd. And there is a recent paper by Schmidheiny and Siegloch that came out that clarifies a lot about event studies. And if you want to estimate a model where you have staggered adoption and you have to choose a time window, I strongly recommend that you read their paper. Because first of all, what they show is that different researchers have very different practices, and there is no common set of guidelines for how to do an event study. So what are some of the tricky things here? So if you are in a world like this up here, where you want to have, where different units are treated at different times, and you want to stack them on top of one another. The question is, first of all, how long do you choose the event window? And what they show is that this is far from innocuous. And the reason is, so we will look into this later in greater detail in a later video. But in a nutshell, what happens is that if you make the event window longer, it can happen that some groups have a huge weight in your estimator and others have very little weight. And so then if you want to look at the average jump, you may get a biased estimate for that average jump simply because your estimator, by construction, changes those weights when you make the event window longer or shorter. So this is something to be aware of. It's not an innocuous choice. Sometimes there's a pragmatic choice, right? So your sample period only goes a certain duration, but even then you need to think about, well, how would my estimates change if I made it longer? The second thing is what to do with data points that lie beyond the leads and lags. Okay, so that lie before the first lead or after the last lag. And what should we do with them? Should we discard them? Or should we actually keep them in the data set and code them in a certain way? And the clear answer here is you should keep them in the data set, and you should apply what is called binning, whereby any data point that lies before the event window is coded with one dummy. Okay? So you don't distinguish whether it's 5 periods before your event window or 10 periods. They're always you lump them together in the same bin, in the same period bin, and you do the same after the last lag. Right, so any period, let's say you have an event window that goes out 3 periods after your event, and then you have observations period 5, 6, 7, 8 periods after as well, and you code all of them as basically one period. Okay, so this is, you just have a dummy for whether that's after the event window. That's what's called binning. And what they show in that paper is that coding is absolutely critical for causal identification. So some comments on the two-way fixed effect difference in difference estimator. So first of all, we need to think about, well, if we run such a model, where does the identifying variation actually come from? Right? You should always take a stand on that, and because without knowing that and without stating that, you cannot interpret your results. Okay? So here it's a two-way fixed model. So you observe different units at different points in time, and you condition on group and or unit and time fixed effects. So all you're exploiting here is variation within groups over time, like in any panel data estimator. So that's the first thing that is very, very important to think about, right? But that makes it also very hard, because now you observe, let's say, a trend in employment in some state, and then you see that the trend changes after they introduce a minimum wage. For another state, you observe the same thing a bit later, and for another state, you never observe this because they never introduced the minimum wage. And now you have those three states. But what is it actually that you compare with what then? Because you no longer have this 2x2 case. And you no longer have this clean interpretation where you just have a 2x2 table and can calculate in a spreadsheet your estimate. Right? You need to use statistical software, run that two-way fixed effect model, and it spits out a coefficient. And the problem is, most people in the literature, even people who publish in journals that I dream of publishing in, interpret their results like the average treatment effect on the treated you get from these 2x2 difference in difference models. But as we shall see, this is actually not how it's done at all. So, but this is how it's done, but this is not how you should interpret these results at all, because it's far from clear how these coefficients can actually be interpreted. Okay, so the appeal of difference in differences is that it's simple to implement. It doesn't have the same many identification assumptions as IV would have, for example, so it's a very flexible model that you can apply to a lot of different contexts, right? But that comes at a cost, and the cost is what we only have discovered really in the last 2 or 3 years. So as of, this video is done in 2021, and it's basically since 2018 those papers have been coming, showing us that the way we've interpreted those different estimates is actually just plain wrong and plain misleading. And so we need to look at difference in difference a lot more closely. That's what we will do. So what I will do first is I will walk you through some examples to show you how it's currently done. And then we'll move back to theory and see, well, what's actually behind those different estimates. So there will be extra examples coming in in an additional video, but here just the application of an event study design by David Autor. That's also one of the textbook examples. So basically what he does there is he has worker level data, and he looks at the effect of employment protection legislation. So basically how easy it is to hire and fire people on temporary employment in the US. And so temporary employment, especially of workers who work for temporary work agencies. So that's obviously an important policy question in labor economics, which is, if you have strict employment protection legislation, does that encourage firms to use more agency workers, because hiring someone is quite expensive, because it will be very expensive to fire them eventually. And what he does there is he looks at court rulings in the United States, in different states at different times. Okay, so as he claims, those court rulings, that the exact timing of those was unpredictable. This could be on a judge's desk for years, and then at some point there is a ruling. And what he does then is he looks at the share of agency workers in these states right before the court ruling, so in 2 periods before, and then in several periods after. And that's an event study design. Right? So it goes back to this idea here, where you have the state at the top introduces the employment protection legislation earlier, the state at the bottom introduces it later, and what he does then is with his 2x2 fixed effect estimator, with this event study estimator, he stacks them on top of one another. But it's not that he goes there and stacks them all on top of one another himself. All he does is he estimates this event study framework. And so basically what we see then is we see the plots of the point estimates and standard errors of those coefficients, right? And so he has 2 pre-periods and I believe 3 or 4 post-periods. So that's what you can see here. And you can see here that there is no difference in the trends in the years prior to the introduction of employment protection legislation. So states that have introduced it and states that have not yet introduced it had no difference in agency work before one state introduced it, but the difference opens up later. Now here you note that it may not be statistically significant, the difference, but you clearly see some things happening in the data. Okay, and that's just an example of an event study design. Tricky thing is that interpretation that I've just given you there, the states that introduced the treatment, their agency work went up relative to states that did not yet introduce that employment protection legislation, is actually not quite what those estimates represent. More on that in future videos. But what we will look at in the remainder of this one is we will look at a case that I believe many of you will find very useful, which is typically we view diff and diffs as a quasi-natural experiment, or a method that exploits quasi-natural experiments that are binary of nature, right? So a state introduces a certain policy. So you're either exposed to the policy or you're not exposed to the policy. So that's binary. But you can do the same with a continuous treatment. The interpretation may be a little bit more tricky, but it's not so tricky. So here the idea is not that the treatment is there or is not there between units, but that it's simply the treatment intensity differs between units and over time. And here one of the standard examples of a paper doing that is Esther Duflo's paper on the effect of school construction in Indonesia. And so this is one of Esther Duflo's very few but also very insightful non-experimental papers, where she looks at the effect of school construction in Indonesia on the education outcomes and human capital outcomes on people in Indonesia. Right? So the idea is if there was more schools, do those people afterwards fare better in life because they had more education? Now what she exploits there is that there was this massive school construction program that was rolled out across different regions in Indonesia, and that varied not only across regions but also over time. So what that means is that some within a place, some cohorts were not affected by the school expansion program because they were already too old, whereas then others were of the right age that they were actually still affected by it. And so here the time variation is not really years, but it's actually, she compares different cohorts in different regions. So it's basically she uses variation across regions and across cohorts. Okay, so it's still a different diff. It's just that the time periods are not time periods as we usually think about them, as in, 1 year, 2 years, 3 years after treatment, but it's more cohorts that were 1, 2, or 3 years too young to be treated or too old to be treated, and those who were in the right years where if a school was built in the area, that would benefit them a lot. So here is the very basic model where she looks at the level of schooling and then has basically here a variable that is continuous for the program intensity, and then for whether then just a dummy for whether a person was of the right age, as in they were young enough to benefit from that. Okay, and then what the estimator compares basically is the trend in schooling in places where there was lots of school construction, and places where there was less school construction. That's one difference. The other difference is they compare young people in those two types of places who were affected by the treatment, and older cohorts that were not affected by the treatment. So it's a 2x2 difference in difference logic, but there's a little more to it because you have now a continuum of treatment types. Right? So you not only have some that were treated and some that were not, but you can think of it as a 2x2 by simply saying, well, there was some places that constructed a lot of schools and others that constructed very little. Okay? She also controls here for region-specific variables, but that's not that relevant. And so this is still the basic regression. It's just a 2x2. But then what she looks at is she basically has here also the equivalent of leads and lags, but here it's really just cohort dummies. Okay, so here you have the interaction of the treatment intensity, how many schools have been built in that year, interacted with cohort dummies. Okay? And the assumption was that within a treatment, within a region, the assignment of treatment was as good as random, or at least people couldn't select into whether they would go to a school that was constructed or not. But especially when older cohorts are the control group here, that's quite a reasonable assumption. And so what's happening here is probably best seen from that graph. So this is the age in 1974, and obviously here those who were in 1974-23 in that sample were the oldest people, and those who in 1974 at the start of that program were 2, these are the youngest people in the sample. And you can see here that for those people roughly that were basically too old, there is no significant difference in schooling between those places that had lots of schools built and those places that did not have many schools built. But that difference opens up when you look at the cohorts that were actually affected by the school construction. Yeah? And so they have significantly more schooling, okay, so 0.2 years on average, for every 1 unit increase in the number of schools or in the percentage of schools. You'd have to look at the scaling exactly. Admittedly, in these types of models, the coefficients, the levels are not always easy to interpret, but if you write a paper, you need to provide some guidance as to how to think about those magnitudes. Okay, but you can see here that there is a significant difference among those cohorts that are affected by the school construction. They have more schooling. Right? There's more that she shows in the paper, but to me this is one of the prime examples for a very nice flexible diff in diff study where you have, flexible means in that case we we allow for separate differences for each time period, in this group, in this case age cohort. And in that sense, those the effects for those cohorts before the program actually happened, or that were too old, are actually almost like a placebo test, right? So if we saw differences there as well, that would indicate that there's probably something else going on, that there is something driving differences in schooling that is not explained by the school construction program, but is correlated with it. And so here, this is obviously quite convincing to say, well, those cohorts have not been affected, whereas the younger cohorts have been affected, and that's where we also see the differences. And the good thing about difference in difference analysis is there are so many papers out there who do this really well and also graph their results really well, and you can always then take some of these papers as a template and really and simply model your analysis following that template. The only thing you need to do is you need to be up to date when it comes to the latest methods, because even papers that have been published 5 years ago, the methods in those papers may already be a little bit outdated, or you may have to add something to the analysis. The logic of diff in diff will always remain the same, but the way we perform the analysis and the way we interpret the results has changed dramatically over time. Now, in the next video, we will look at a few more examples of diff in diff analysis.